Welcome back, nerds. Boink. Section 2.3, polynomials of higher degree with modeling. So we're going to be doing a lot of the same stuff that we were doing in 2.2, only now they're not just second degree polynomials like quadratics. They can be third degree, fourth degree, fifth degree, and so on and so forth. But it's all generally the same ideas. So the whole modeling part, yeah, word problems, they're not going anywhere. And today I'm going to be showing you how to do some stuff on the calculator. I mean, I'm pretty sure you already know how to do it. But I'm just going to show you again. So I think you already know. Alrighty, there's nothing in this box that's new, so we're just recounting what our vocabulary is. A polynomial is a string of terms that are held together with pluses and minuses, where all of the exponents are positive whole numbers, and it's in standard form. As long as the thing is written in the order, that makes the exponents count down from big to small, and even at the end, you might have no x at all, so no exponent at the end. I've already said the word term, that's all the individual pieces. The numbers, the a sub, n minus ones, whatever, the numbers that sit in front of those x's, those are your coefficients. And when it's in standard form, the term at the front with the leading term, and the number in the front of that x is the leading coefficient. And the biggest exponent is the degree of the polynomial. That leading term is a pretty important concept in a moment. For now, we're going to do more transformations. So this lesson starts exactly the same way the last lesson did. I think we were transforming cubics or something. Or no, quadratics, didn't we? It was the parent function, right? X squared. Okay, this one we're going to transform the parent cubic, and this one we're going to transform the parent fourth degree polynomial. But the good news about transformations is that's not different. Transformations work the same on everything. That's why we like them. The parent cubic. I should have put this on here as a dotted line like I did with the quadratic, but I forgot to. Not going to lie, I just forgot. So the parent x to the third graph. Be careful. Your y-axis goes by 2's. Be careful. Y goes by 2's. Okay. 0 to the third power is 0. 1 to the third power is 1, which is halfway between 0 and 2. And 2 to the third power is 8. There. Now we go to the left side of the x-axis. Negative 1 to the third power is negative 1. Negative 2 to the third power is negative 8. There it is. All right, so I'm going to put this on there as a dotted parent function. There's the parent cubic. While we're looking at it, I'm going to remind you that this is a function that is increasing over its entire domain according to AP. To the left of the center, this graph is concave down. To the right of the center, this graph is concave up. And instead of saying the center, I should probably use some good vocabulary. The point where our graph changes concavity is called an inflection point. In fact, anytime concavity changes, you have an inflection point. I think we talked about that earlier in the year, but I wanted to bring it up to highlight what's going on with this cubic. All right. Skirt. Time to transform it. Hey, what's happening? Oh, they're sharing a bag of chips. I bet money you can hear that bag crinkle on this video. Oh, I don't care. I'm just saying. Give him a chip. He wants a chip. Where's my chip? No, I don't want a chip. I'm good. Transformations, we know how to do this. This x plus 1 on the inside, this tells us horizontal inside, opposite. I have chips in my lunch. I'm good. This is shift left 1. And vertical outside, same. This multiplier on the outside tells us multiply our y values by 4. That's going to make them really, really large. Vertical stretch, factor 4. I don't know why I have so much space here. I don't need that space anymore. Maybe it was for point trees. But I don't need a point tree for this one. Because there's only 2 transformations. So let's oh, she's still looking. Sorry. let's go to my vertex. I'm going to shift it left 1, which puts it here. Sorry, not vertex, inflection point. Anyway, shift it left 1, that puts it here. Its y value was 0, so when I multiply that y value by 4, I still get 0. So my inflection point is still on the x-axis. Cool beans. Chilled legumes. What are you doing over there in the corner? What's he doing? He's charging a phone on my wall, isn't he? I'm gonna glue those little safety things into all the sockets around the room so nobody can use my sockets except for me. I got sockets behind me. Why would I need the sockets around the room? I'm always back here. I said glue it in. Well, you're supposed to charge your phones over there in my charging station. That's not my problem. You mean the school's laptops? They're charging right now. Then they don't use that laptop. Then they can charge it at home. Alrighty. Let's take this point right here. Shift it left 1. It goes right there. However, its y value is 1. We multiply that by 4, and we get a y value of 4. Goes right there. And this coordinate right here, we shift it left 1 unit, which puts it right here. Underneath this -2. This has a value of -1. We multiply by 4. Now it has a value of -4. Did I mess something up? Okay. These points, unfortunately, when I multiply their y values by 4, they go up to 32, which my grid does not go up to, so I can't graph them. Basically, what's going to happen is this graph is going to get really, really steep. So it is still an inflection point right there, because it does change concavity from concave down to concave up. It's just harder to see. It's just harder to see, but it is an inflection point. Yep. All cubics have an inflection point somewhere. We good? Easy peasy? Fine. Let's do one with more transformations. Oh, this is a 4th degree polynomial. Do you guys know what a 4th degree graph looks like? It doesn't have to be M-shaped. They can be M-shaped. No. Let me show you. And unfortunately, I forgot that I wanted to fire up OBS. So, not necessarily. All right, so you guys in the room can see on my screen right now Desmos, but the camera can't, but that's whatever. In the meantime, I'll just do like cool things underneath the camera and, But anyway, so on Desmos, I've got a quadratic up here. Right? What did I do under the camera? I just moved my hand around for funsies. Anyway, right now I have this set up as x squared. See it? I have this b is 2. Watch what happens as b grows by 2's. So that next time I move this little cursor here, it's going to become a 4th degree polynomial. Boop. So what did it do? It just rounded out, really. It flattened the bottom, but it made the endings more steep. Watch what happens as it goes up by 2's even more. Why does it do that, he says. Darn near rectangular as the exponent gets really big, huh? If you had x raised to the infinity, which isn't a thing because you can't, infinity is not a number. So if we said, so back to the screen that is actually going to have writing on it. You don't need to know this, but if you are curious, the limit as b approaches infinity of x raised to the b is this shape. You don't have to know that. But if you could have an infinite exponent, yes, it would be a perfectly flat bottom with vertical sides. Isn't that neat? It's actually really kind of cool. Huh? No. Can you graph rectangles? Yes, but easier than rectangles is squircles. Squircles are like squares where the corners have been rounded off. She says, I hate math. I don't know if squircle's a real shape, but the video that I watched on it, that's what he called it. It was really neat. Anyway, So we have the parent fourth degree polynomial, 0 to the fourth power. Oh, wait. Now we have the fourth degree polynomial. 0 to the fourth power is 0. 1 to the fourth power is 1. 2 to the fourth power is 16. I couldn't actually get it to fit on the grid. Negative 1 to the fourth power is also positive 1. So like you saw on Desmos, for those of you that were in the class and not just trying to watch the videos, it's like a parabola, but it's flatter and then steeper. So it's flat and steep. There we go. Look. The reason why it does that is because if you raise a number between 0 and 1 to a power, it actually makes the number smaller. It's like 1/2 squared is 1/4. 1/2 to the fourth is 1/16. So that's why. So it makes your numbers between 0 and 1 smaller. So it flattens it out. And then after the number 1, every time you raise a number bigger than 1 to a power that's bigger than 1, it gets bigger and bigger and bigger. That's why. In fact, if we went to Desmos, let me go back to Desmos real fast and show you something different. If I did this, let's get rid of that. Let's say x squared, and then x to the fourth, and then x to the sixth, and then x to the eighth. I'm hoping you can see that well, those of you that are actually in the classroom, you could see that as the exponent got bigger, the graph flattened out on the bottom more and more and more and got steeper and steeper and steeper. But look which point they all go through.
0, 0.
And 1, 1. But yeah, so they all go through the same vertex. It is technically a vertex. And then they all happen to go through this 1, 1 and negative 1, 1. And the reason why is because numbers between 0 and 1 raised to powers get smaller. I am so happy. I'm a freaking nerd. Yeah, what's up, Adi?
Raise it to 1/2, would it make it wider?
Well, the 1/2 power is a square root. So that'll turn it sideways. So fractional powers turn it sideways. Like third roots, fourth roots, fifth roots, half roots. Well, because he wanted it to make it wider, and I understand what you're getting at. It doesn't make it wider. Yeah, because it wouldn't be. Yeah, it breaks, unfortunately. Because the moment the exponent dips below 2, things start to get a little weird. Yeah. I can. If I do x to the 200, it actually makes rectangular shape. I tried it earlier. Now, it's not rectangular. If you zoom in really close, you can see that it's not. But if you make it to the 2000, I mean, I don't know how close we'd have to get. Okay, we had to get really close so you can see it start to break. You know, it's too bad that didn't make its way to the video, right? All right. Anyway, so if you're watching the video and you don't know what to do, go on to Desmos and start changing the exponents to higher and higher even numbers and watch the magic occur. Anyway, let's transform this bad boy. I see a shift right 2 units. No, I did not say that. I said shift. Oh, okay. Shift right 2 units. But for the y's, remember, outside changes follow the order of operations. So we're going to multiply by negative 1, which makes our positive y's negative, which is a reflection over the x-axis. And then we'll shift up 5. You can't handle them? Oh, you can. Oh, okay, cool. I was like, why? They're always the same. Let me write. I'm gonna use an XY tree for this one. Just because the 2 transformations kind of break my brain a little bit, so I'm just gonna use a point tree. The original coordinates were negative 1, 0, 1, and they went 1, 0, 1. We're going to transform this thing to get a new orange graph. For the x's, it's really easy because it just says shift to the right by 2. So if you're on the x-axis and you go right 2, your number literally got bigger by 2. So we just add 2 to all of our x's. There, that was easy enough. But for the y's, what we have to do is multiply our y value by negative 1, and then we have to add 5. So we'll take this y value, 1, multiply by negative 1. 1 times negative 1 is negative 1, and negative 1 plus 5 is 4. Well, this thing is symmetric, as you can see here, so there's also a 4 here. And 0 times anything is 0. 0 plus 5 is 5. There it is. Remember, flat at the bottom, steep on the sides. 1 comma 4. No, it's this times, not minus. It's okay. 2 comma 5. 3 comma 4. Flat on the bottom, and then steep. Hey, come on now. There we go. It's actually steeper than what I drew, but whatever. There it is. You have one of those in your homework.
Okay.
I don't feel like bogging you down with extra stuff that does the exact same skill. Transformations, we're going to do them a lot all year long, so I'll just try to give you, they're simple, right? I'll just try to give you like one transformation question just to keep them fresh in your mind. Can I flip the page? On the back, we were asked to find the extrema of this cubic function. Extrema, maximums, and minimums. Maximums and minimums. First, before I touch my graphing calculator, solving by factoring. What makes this polynomial equal 0? What values of x, Adi? Negative 3, 1, and 2. There it is, because it's whatever makes the insides equal 0. So negative 1, negative 2, negative 3, x equals 1, x equals 2. If we were to distribute all this crap out, the front term would say x to the third. Positive x to the third. Which means it's going to kind of have a shape like this, positive x to the third. At least it will in the edges. Notice I didn't put any numbers on my y-axis, because I don't care. It's going to look like this. Just like that. And we're going to put that on our graphing calculator in a second to see that. What we are hunting for are the coordinates of a maximum, well, any maximums, and the coordinates of any minimums. And we will need to be able to label them as maximums and or minimums. Cool? Can we pull that off? We're going to find those values with our graphing calculator. But Mr. M, aren't they just halfway between the zeros? No, they're not. Okay? They're just not. This graph has one minimum. This graph has one. Wait, I switched my color. Hold on. Red is maximum. Sorry. My graph has one maximum. My graph has one minimum. We're going to get the xy coordinates of it. Bloop. And I'm not going to distribute this thing out. I don't care what it is in standard form. I'm just going to type it the way I see it. So x plus 3, x minus 1, x minus 2, like that. And I'm going to hit zoom 6 because I don't know what the last graphing window was that I was working with. So zoom 6. Oh, okay, it almost got all of it. I can see this maximum is above the top of my screen, but look at all this real estate I have down here that I didn't need. So what I'm going to do is I'm just going to shift the entire window up by, like, say 5. So go to window, and on my y scale, my y minimum, I'm going to bring it up by 5, and I'll bring my y maximum up by 5, and that's all I need to change. I should be able to easily see the maximum and the minimum and all the zeros when I hit graph. I just changed my y minimum to negative 5, y maximum to 15. That's still a span of 20 digits. That's all I changed. And we hit graph. Probably because you have a stat plot turned on again. Go to y equals. If you have a stat plot, shade it in. Go up there, highlight it, hit enter to turn it off. Was that the problem? Okay. My x's are normal. My y's went from negative 5 to 15. So picture not drawn to scale. Whatever. I got the general idea, right? Alrighty. Let's find our maximum and our minimum. We use that with our calculate menu right here under well, above trace. So second, trace, and I'm going to go for the maximum on the left. Hit enter on maximum. It says go to the left. I'm like, all right, let me go to the left of this answer. So it's like over here. Now go to the right. Go to the right a little bit. Hit enter. Then guess. So get close. This is somewhere in the middle. Hit enter. Got it. My maximum occurs at the coordinates negative 1.528. Oh, my phone is not on vibrate. Comma 13.128. We're going to find the minimum the exact same way, but instead of doing second trace maximum, we do second trace minimum. Second trace 3, and the whole left, right, center thing. Yeah, that's to the left of the answer. Hit enter when I'm on the right, go to the middle, hit enter. Boom, found it. We have a minimum at 1.528, comma, negative 1.128. Mr. M. The maximum and the minimum, are they always going to be the same number, one positive, one negative? No. Why did that occur on this one? Because every cubic has an inflection point which will perfectly cut the graph in half. This inflection point happens to be on the y-axis. So we get to review once again on how to find the inflection points of a graph. We will estimate inflection points by saying it's the average between the x's. That's how we're going to have to do it for anything above a cubic. For cubics, the inflection point will always be, and I hope what I'm saying is, I'm pretty sure I'm 100% correct on that. For a cubic, the inflection point will always be the average between the maximum and the minimum x values. But for other polynomials, the best we can do is estimate it by using an average. It's only guaranteed to be an average on a cubic because all cubics have an inflection point and they are all symmetric, so to speak, around their inflection point. These ending also in a 2/8, yeah, I'm pretty sure that's a coincidence of the way cubics work. But that's how we use our calculator. All right. How many times did this cubic hit the x-axis? 3. Was it guaranteed to hit it 3? No. I could have shifted it up, and I could have made it so that there was only 1. I could have shifted it up enough so that this bump was actually happening up here. But there's no way for me to make it have 0 answers. Every cubic will have at least 1, because one of the endings is always going to point down, and the other one's always going to point up. My point is, though, was there a way for this cubic to have more than 3 solutions? No, because the solutions come from the sets of parentheses like that. So a cubic could have at most 3 solutions. How many extrema did this one have? It had 2. Is every cubic guaranteed to have 2? No. These cubics have no extreme values. How many inflection points did it have? It had 1. Is every cubic guaranteed to have 1? Yes. But that's just a property of cubics. What was I getting at? My point is, for any polynomial, as long as the exponent is 2 or bigger, because otherwise it's linear. So if you've got a quadratic, a cubic, a quartic, a quintic, anything like that, any power bigger than 2 or bigger, then your polynomial has at most in, bless you, at most in zeros. That means at most the highest degree crosses of the x-axis. At most, the degree of the polynomial minus 1 extrema. This one was a power 3 with 2 extrema. And at most, the degree of the polynomial minus 2 inflection points. And the reason why this is occurring is because, I'm just going to draw a really, really basic picture for you, okay? Let's say my graph has 3 solutions. Did you notice that all of the extrema occur, but I want to say solutions, let's use a better term here, zeros. Did you notice that the extreme values always happen between the zeros? They're not always below. I'm just showing you a between setup. So they're going to be between them somehow, right? And did you notice that the inflection point happened between maximums and minimums? So that's why it goes in -1, in -2. Because anytime you go between values, you subtract 1. It's like you hold up your hand, you have 5 fingers, but how many spaces between fingers do you have? 4 spaces between fingers. So when you go between things, it subtracts 1. She's counting. Okay. It's a good thing she wasn't wearing mittens. It might have slowed her down. Get it? Because mittens are like this. They don't have fingers. I was just making sure because nobody chuckled. Yes, gloves have fingers, mittens don't. That is the difference. What? Okay. I know, right? Just gonna poop on my joke? I called you dumb. I insulted you. I said it's a good thing you weren't wearing mittens. It would have slowed you down. Because you're the one who said it. Because you counted. Because you counted. You spread your fingers out to count. Anyway, because it's funny. I learned that's an old insult from a show that you're probably too young to even remember. But Roseanne. But anyway, at one point in time, one of the kids gets a job at the grocery store, and she's the checker at the express lane, you know, where it's 10 items or less. And the sister's like, oh, don't wear mittens, it'll slow you down. Meaning she's too stupid to count to 10. Because mittens, you'd feel like you can only count to 4. I don't know, I liked it. I thought it was funny. I don't need you to like my jokes. Okay, guys, so let's talk about end behavior. End behavior of a polynomial tells us what the endings, so to speak, look like. And there are 4 options. And the reason why there's 4 options is because it's based off of 2 things. The first thing is the degree of the polynomial even or odd? And the second thing is the leading coefficient positive or negative? And since there are 2 things with 2 options, it creates 4 scenarios. All right, 2 things, 2 options, 4 scenarios. Right here, what we have is odd degree, odd degree. That's what we got going on up top. When the degree of the polynomial is odd, notice that the endings point different directions. Different. And I called her dumb. Different directions. And again, because the degree is odd, different directions. The endings will point different directions, one up, one down. So what determines left or right? The leading coefficient being positive or negative. If the leading coefficient is a positive number, like you see here, then over time, this graph will have a positive average rate of change. So it'll grow from left to right. Left down, right up. But if the leading coefficient is negative, this roller coaster overall has a downward trend. So a negative average rate of change. Once again, if the biggest exponent is an odd number, the endings point different directions. If it's positive, overall it's an upward trend, so positive average rate of change. If the front is negative, overall it's a downward trend with a negative average rate of change. Comfortable with that idea? Nope. So what happens if the degree is even? Like with a parabola or a 4th degree polynomial. We all saw them. When the degree is even, they point the same direction. Yes, you learned this last year. Somebody admitted it. Hey, the phone is ringing. Man, that's just annoying. Okay, so anyway, what about if, how do we know if they're both up or both down? Remember me telling you that positive people smile and negative people frown? Positive people smile, so the endings point up if the front number is positive, and negative people frown, so they both point down if the front is negative. There, okay? There it is. So we use the degree to tell us if the endings point the same direction or opposite directions, and we use the leading coefficient to determine that behavior. Let's do... No, we have time. You kidding me? I'm using up this time, folks.
Are you not happy yet?
Well, we're not going to have time. It's unfortunate. I'm going to do this question, and this is where we're going to stop.
Okay. Go for it.
All right. It says, describe the end behavior using limits. Then use a grapher to graph the polynomial that shows extreme values and all that crapola. It doesn't say find them. It says just show them. Fine. Let's use limit notation to describe the end behavior. First, is the degree even or odd? Degree, I'm glad someone's listening. Degree of 3 is odd. That means my endings point, same or opposite directions? Opposite directions. I'll use the word different because that's what I wrote. And the number on the front is a positive 1. What that means is it has a positive average rate of change. So my graph is down as it goes to the left and up as it goes to the right. And I don't know anything about the spaghetti in between. I don't really care. The point is this is what the far left and the far right will look like. Let's fill out that limit notation. As I go to the left, x is heading towards what number? Negative infinity. So we say the limit as x approaches negative infinity. As my graph goes left, my graph goes down. What's down? Negative infinity. This one, as my graph goes right, so right, x goes to the what? Positive infinity. Then my y values go up to positive infinity. And the last thing we were supposed to do was just draw a graph so that we could see the extreme values, right? Well, I'll tell you what. Check this out. X raised to the 3 plus x. Oh, hold on. Plus x. Zoom 6. It has no extreme values. So it's just, it looks like a standard cubic. It's not, but that's what it looks like. So because it has no extreme values, I'm not even going to bother drawing it. And before I throw the nerds paper on here and say, you know, thanks nerds and stop the video, I think it was Mark had a question. What's up? Oh, the homework. Yeah, all right. Nerds.